hear anything from you? For some reason, no.
No.
I don't know why.
Can you hear us now? Devi togliere le tue casse.
See, am I getting any audio?
Can you hear us now? Can you hear us? I think not. Ok, ho disattivato le mie casse e il mio microfono. Quindi riattiva le tue casse e il tuo microfono.
Hold on just a second. I think I might know why. Maybe. Why can I not? Let's see. Oh, there we go. Now I can hear anything.
Okay, can you hear us?
Yeah, my tab was muted for some reason.
Okay, perfect. Are we waiting for the file of record?
Yes, we will need the flyer record to be in the meeting.
Okay, I sent him an email like 3 hours ago. So it is late, or I can just send a new email. I can try. Just hold on a second. Okay, I sent him an email, so I think in a while he will have the call. If you want to ask something now, we are ready.
We'll probably want to wait for him.
Okay. Okay, just in case, I have his telephone number. So if you want to make him a call, I can share with you the cell phone number. Okay. Okay, Eric, if you want to make him a call, I'll share on the chat the telephone number. Okay.
Is this a cell number?
Yeah, I shared it on the chat.
Okay.
If you want to make him a call, that would be better.
Okay, we'll just give a second for them to for Adam to respond. He's in Colorado, so it's during the day for him as well. Okay. Let's. We will utilize what time we have while we're waiting for him to respond by going through just a bit of the rock as it currently stands. Is that what I'm seeing behind you?
Yeah, that's the rocket.
Okay.
You can see it well. So if you want to begin with something specific, just let's see. If not, I will start from the bottom and.
Yeah, let's start from the bottom.
Let's see. Well, first, I would like to introduce you the other that are in this call. So, behind me, I have Leonardo, that's the electronics referee. Here, Joelle, that's the expansion. Expansion referee. Here, Enrico, on the back. Re-entry. Next, I have Valerio that's on the bottom, and the structures referent. So I think we can begin from the bottom. So the bottle and the fin canister, I will give to Valerio this. Yes, and he will.
Just to, you will need to record this, by the way.
Yes, we're already on.
Now that we've actually started.
All right.
Okay.
So as we said, we're starting from the bottom. All right. Can you hear me? Can you hear me? No.
Better. Yeah.
All right. So no, devo parlare attraverso il tuo microfono, Max. Can you hear me? Max, devi accendere il tuo microfono.
Come here.
Spegni il tuo. Spegni la tua cassa, spegni il tuo microfono, l'hai fatto? Right. Sorry for the inconvenience. So, can you hear me now?
Is the meeting being recorded now?
Yes, the meeting is being recorded.
Okay. All right. You will need to submit that, by the way.
What?
You will need to submit it once we're done.
Understood. So we're starting off from the bottom.
Mm-hmm.
So this is the end of the rocket. This is the boat tail. So the main body ends at this line, and from here on, it's our own made fiberglass shape, which is an outside skin, 8 layers thick. It's very thick. It's very sturdy. It's very impact resistant as well. On the inside, there's a ribbed frame of aluminum, which is joined to the skin through 4 M3 bolts, which go through the skin itself. Right now, the holes are not drilled in, but they will be like tomorrow.
And that goes up against your fin can, right?
So actually, this does not quite go up against it, but it will go like this, because the outside body lives on top of this. It will go all the way to the fin's bottom, and it will screw onto the main body itself. So actually, if you notice, you'll notice that both the main ring on top of the boat tail and also the rings of the fin canisters are of the same design. This is
Mhm.
where so we can manufacture more spare parts with fewer designs. So moving on, if we move on, all right. So
Also, how does the boat tail like you said that it bolts through the skin, the airframe?
yes. So
Does it also connect to the fins? Because it
no, it
looks
is
like
not
it does.
connected to the fins themselves. It is connected to the body through 4 bolts like this. So it
Okay.
will sleeve on like this, and it will match the holes.
Oh, okay, yeah.
And then you'll screw
How is the aluminum structure connected to the boat tail?
the aluminum structure. Oh, so on the inside there are 4 3D printed pieces. This we're planning to print in a carbon filament. So in a filament which has got carbon filament inside, so it's very strong. They're threaded with threaded inserts, and bolts are screwed into the inserts, securing the boat tail onto the shape. Also, the inside skeleton is itself very tight fitting to the boat tail, and this is of course custom made to this exact shape, so it will transfer the load very well, we believe.
And where does the thrust ring for the motor sit in relation to the boat tail?
So the way the no. In relation to the boat tail, so actually the way we distribute thrust from the case, you're talking about correctly.
Yes.
Can I have the case?
Okay. So, yeah. Let's see. There's a slight.
So the way this works, so basically we're taking the thrust from 2 points, but mainly from above. So
Okay. So
later on we will get to a thrust
you're
ring.
bolting it into a bulkhead further up in the airframe.
Yes. So the main
And-
thrust bulkhead is up above. Although there is also a system that does catch on this lip.
Yeah, I did notice there's a slight increase in diameter, so that would catch on the boat tail, but most of it would be transferred up into that bulkhead above the motor. Okay.
Yes, so we believe that the nozzle will load onto the liner, which will load onto the top enclosure, which itself will load onto the threads of the main thing above, and on top of this we have put a bulkhead, which will take most of the load, which we will see shortly in the tour of the rockets. Should I move on to the fin canister?
Yes, let's go ahead and move on to that.
So the fin canister is made of 4 milled aluminum 6061 pieces, rings. So each of them is reinforced with this kind of rib, where
Okay.
to avoid flexional loads, which would snap it otherwise. The fins are secured with 4 bolts and nuts, and the fin canister itself is secured to the body the same way the boat tail is secured to the body, so through 4 times 4, 16 bolt connections to the body itself. And of course the case fits snugly inside of here, which will also help keep center the motor case. For extra rigidity, we've added these spars of carbon fiber, which go to reinforce the fins at the root and also distribute the load as well.
Okay, so the connections with the fins go through those.
Yes, so if you can see better, the fins and the spars overlap. So it's thrice as thick as on the main fin, and then they are clamped by the aluminum bits which protrude from the rings, and the bolt is put through the hole and thus secures very strongly the fin onto the 4 individual rings.
And you've accounted for like vibration forces with this, I assume.
Yes, we're planning to use self-locking nuts. So we're very confident.
But there are quite a few of them. Even if one of them comes loose,
yeah, of course we've also
you would just have a piece of
Yes.
So the fins would still stay connected even if 1 or 2 of them were to come out. Since they're let's see, you have what, 5?
4.
4 per, so that's 4 connections per fin. Yeah. That's 2. all correctly. There we go. Okay. And the fins are carbon fiber.
Correct. They're a 3 mm thick carbon fiber laminate, which we did not make ourselves, so it's industrial grade quality.
Okay. All right. Since we're on the fin can right now, what is your currently calculated fin flutter velocity?
So I'll jump back. I'll give the call back to Massimo, which will discuss this part. Quindi io ho spento.
Okay, can you hear me?
Yes.
So, can you hear me?
Yes, I can hear you.
Okay. So, regarding the fin flutter velocity, we used the notorious NACA model, so the technical note 4917, if I couldn't get it wrong. And the flutter velocity is like 2.9 Mach. In terms of velocity, it's like 950 meters per
Wait, did you
second.
say Mach 2.9?
Yes, they're pretty stiff because even if 3 millimeters, give me the canister.
Okay, so that's about like 950 meters per second.
Exactly. It was like a surprise, but here we are. So Mach 3, and we are flying at like maximum Mach 0.9. So we are way below the limit. And for just
And what was the reference you used for that?
sorry, what?
What was the reference you used for calculation?
Reference the NACA technical note 4917, the famous one. That's the model that pretty all use. But we made another calculation and we implemented a numerical model on Nastran. Sol 145, that's the flutter analysis solver of Nastran.
Okay, that's the revisited one. So they've. Okay, yeah.
Okay,
That was the one where they made the correction.
Okay, and we didn't get a flutter velocity because Nastran student version has a limit that it cannot study like flutter velocity over Mach 1. But we got pretty long range between like a more or less 20% more or less than the maximum velocity in flight. And I don't know if you have seen our technical report that we uploaded yesterday. I think not.
I did. Yeah, I did read through the third progress report.
Not the first progress, but the technical report, because here is explained a little more well. But even if the third, I think the second progress report is explained more in detail, and that's what we have done regarding the flutter. So we are way below the limit of flutter, and
yeah, anything like if you calculate anything above Mach 2 for a fin flutter velocity, then yeah, that's because I mean your 10K. It'd be. I mean, you could get your rocket to go fast, like Mach 2 speed. You won't reach. Well, you will reach 10K. You'll surpass it. Because it's very hard to reach Mach 2 and slow down at 10,000 feet.
We don't have that problem because, as I said, our maximum Mach is like not even Mach 1, so it's 0.9.
Yeah,
so next, I think we can pass to the air brakes or the crash ring. So,
okay, so this is the lower airframe.
Yes.
Yes.
We're going to be trying to show.
Okay. So is that where the motor connects to?
Exactly, yes.
Yeah, there's a hole in here.
Okay, move it a bit to get, there you go.
That's at the bottom of the air brakes block.
Okay, yeah, that's
Yeah,
that's definitely not going to come loose.
All the way. Yes. Okay.
So
Yeah, so that screws in there. Yeah, that'll.
and then they make contact, and this way the thrust mostly loaded here, which is our designated thrust ring, which then transfers the load to
Mhm.
bars onto the rest of the airframe, and itself is because of the connection and the connection here will drag the rest of the bottom half of the airframe up with the vehicle.
Yeah, so the thrust is transferred through that metal coupler.
Yes.
Another couple that goes onto these metal bars that's still made. So are the four stringers, we can say. But I don't know if you can see here, that's the avionics bay, and run through the avionics bay. And,
What is the avionics bay made out of?
or carbon fiber reinforced 3D printed material, so it would be pretty strong. So
I mean,
here,
none of it
it's not structural because, as I was saying before, we have
Oh,
first
so those rods go all the way through.
steel made that goes all the way through the body
Okay.
and the expulsion bay. So where the expulsion is. That's just a mock-up. Here behind we have the real expulsion bay, and if you want, we can continue on this.
Let's go back to the lower airframe itself. So
Okay.
you showed me like the interior section. So where is the body tube that connects at that point?
Okay. So just a moment. Here we have the other shell. We took off one.
That's the upper airframe where the
upper
payload
airframe
is and stuff like that.
is-
Where's the lower airframe? Like where the fins would
got the
go?
lower airframe here. So basically, the rocket is divided into three airframe pieces. So there's one, then it's split into a meter 30, which is whole again, a cylinder, which goes all the way to the. So the way this here is the lower half, which is it's also got the slots for the fins. Will basically go onto here. And go on. So it's held on by 16 joints, 16 ball joints M3, which are this ring and this ring. And we believe this gives us, I mean, this length here was designed such that it would make it very easy to align. So were they any closer, it would be difficult to line the body. But this is we judged it to be a long enough size that it gives us sufficient leverage to say to keep it straight.
Is there any reinforcement on those holes?
Well, those holes are drilled into very thick.
Not on the metal part, but in the airframe. To prevent any tearing or.
No,
but the airframe itself is very thick.
It's like almost 2 millimeters thick, and we used pretty almost the same tube last year for another rocket.
And there wasn't any issues with damage of the material along the hole?
No tearing, nothing. It was pretty strong. It's like fiberglass. Yeah, it's custom made by a specialized shop here in Italy.
I would like to remind that basically the load applied to these 16 joints right here is only really the inertial load of the lower half of the frame being pulled up through by the thrust ring when the load is on. And I mean, anything else is kind of negligible compared to this initial load.
Yeah, since it's not holding the thrust load directly, it's just getting pulled, and the number of connections would mean the individual forces are low. So
exactly, yes.
Yeah.
Last year we used a very similar design for a similar rocket. It was a lighter airframe, thinner,
and we actually used, instead of 16 M3 balls, we used 16 M2 balls. And the connection was still significant, was still very strong.
Okay.
Next bay. Okay. Here we have the payload bay. So it's not a common form factor because it's a scientific experiment and it's meant to participate in the SDL payload challenge, if I get it right, and consists in this steel box that contains an experiment on GNSS. I think Leonardo.
Yeah.
So based on its placement, this is not deployed.
No, it's not deployed, it's fixed.
Mhm.
Because we have the body that sleeps on and it's closed for the whole flight. So this won't come off.
Mhm.
It's pretty stiff.
Very briefly on the experiment, it's a GNSS receiver with two antennas, and it's logging the signal that it receives by the GPS, and after the flight, after it is recorded, we will analyze the signal to try and reconstruct the trajectory with centimeter level precision. And also, we hope that the distance between the two antennas is enough to have an acceptable precision on the attitude of the rocket itself. So we can compare it with the data that is logged by our main avionics board and compare both of these data sets with the simulation so that we can improve models of the robots.
Okay.
There are no boards in the payload right now because we are conducting a long duration logging test of the whole system so that we can assure that it will work for the flight from the initial duration of at least 5 to 6 hours.
Okay.
Right. So that's the whole thing about the payload bay. If you want to go up and
So a couple other things on the payload. What batteries are you using in the payload?
batteries, I
It's
think
lithium ions, the same batteries that we use for the avionics, but it's in that case it's a battery pack that comes to us already manufactured. So it has current limiter chip and also an over discharge protection, so that even if it takes a very long time to recover the rocket, the electronics will safely shut off on their own.
What I'm trying to what I'm trying to get at is if I can find. Oh, come on. Here it is. So what type of battery is in the payload?
It's lithium ions, cylindrical cells. It's the 21700 type of cell.
So lithium.
Ions.
yeah.
Okay. Right. Yeah. So cylindrical, metallic casing.
Yeah.
Okay. All right. That's good. Perfect.
Same type that we use for the other scale.
Also, all the batteries are the same type.
Different combinations with different capacities and in the different configurations. Some are single cells, others are 2 cells in series, and the battery pack that is in the payload is 2 cells in series with 2 cells parallel.
Okay. And what is the weight of the payload?
It's so more or less 2 kilos. Just a bit more if I get it right.
Well, two kilos is the minimum that we
It's
ask
pretty
for.
lightweight. Yeah.
Oh, trust me. When I was a competitor, our payload, if we didn't include ballast, was like 300 grams.
Ah,
Because it
I
was
remember.
literally just a collection of electronics and a couple of batteries.
And
So
I
we
still
literally
was
just
like,
put everything, like all the actual payload, in like this plastic casing, and then we stuck that inside of a steel tube in order to get it to 4 kilograms.
that's a common solution because okay, because even us yeah, still
Anyway,
frame.
yeah. Yep.
But in reality, it's like half of the mass,
Mhm.
because even the batteries and the electronics are I would not say pretty heavy, but it has a good percent of the mass of the payload.
Well,
So
if the steel is structural, then that's part of the payload, and that technically
Yeah.
wouldn't be ballast.
That's structural.
Mhm.
It's a structure. It's not that weight. Because we had another problem with the payload because here, if you can see, it's like
Move it to because I'm
no,
seeing it
this way.
off
It's
to
like
your
a,
left.
a bit asymmetric on this side because we have two antennas here and here, like square antennas, like
Yeah,
they
actually,
say.
with their own casing that are about 15 millimeters thick, and they have a magnetic mount. So we're leveraging the steel to mount the antennas that are then secured with also with zip ties, so that they don't move with the inertial moves during the transfers.
Well, we had a practical reason to choose the material from the frame, and because the payload inside is delicate, I would say. So we need something stiff to dampen more or less the vibrations. Because that's a practical reason. Just to say.
Mhm.
So move up, or do you have some other questions about today?
Let's see. Let's see. This is related to the section that we're looking at. So for the sections that separate, what is the shoulder length?
Let's separate. We have only one separation, and
So on the vehicle, there's only one separates, and it's the shoulder and the ogive assembly, which slide out of the upper body frame to release, and, to make way for the release parts of the parachutes.
Fantastic.
So this year, the shoulder, which is over 50 is long, which is above
Yeah, that-
1.5 diameter.
It's actually longer than I think that's 1.5 calipers
Yeah,
ish.
yeah,
it's a bit less actually, but it's very slightly so. Definitely above one, very close to 1.5.
All right. Mhm. And from our previous discussions, that's held by dynamic pressure, and despite all the commentary on it,
Okay,
I think
so
most of it is because it's you don't need to go into the discussion again. I understand. It's mostly
because we have
because
another issue we would like to discuss now, and
yeah.
so, it's real that we don't need sharp pins because it's lightweight. This thing is like half a kilo, so it won't come off for drug separation. But we noticed with some tests, some ejection tests, that the sharpins let the inside vein pressurize better, so the nose would come off if, like 4 or 5 times the velocity we have with no sharpins, because if nothing retains the nose cone inside the body, the pressure of the CO2 systems won't build up. So with no sharpins, the nose cone would have just the right pressure to pop off in this way. Not much. But with sharpins, we would have 10 meters per second that is pop off. So actually, we can mount both, so both the solutions. But I don't know if you prefer the solution with the sharpins.
Well, I think most of the discussion and the reason I originally brought it up is because this is the first time I've ever seen a team not use shear pins.
It's time. Okay,
So
because
it's
last
new.
year we didn't use them and it was fine. But
New to the competition, I should say.
it will be better. So that's a green flag for the sharpins.
Let's see. Okay. Actually, this is what we're currently looking at, the nose cone. Is the nose cone made from the same material as the boat tail?
However, it is slightly thinner, but it still has reinforced on the inside. Actually, the difference between the bottle, because it's got to have a very sharp point. The tip is actually made out of aluminum. This was really simply because we cannot laminate such a sharp tip.
No one, even no one who does SRAD, or even like if you look up COTS nose cones, large COTS nose cones, the ones that are made of fiberglass or carbon fiber, they all have metal tips, and that is the reason why, because it is extremely hard to manufacture fiberglass that goes to a point.
Yes, and also if it gets blunt, while we can swap out, we got multiple of these. We only have to go 2 of these, so it's much easier to replace only the tip than the whole origin if it gets blunt.
And nothing is contained in the nose cone. It's like your bulkhead goes all the way down to the end of the shoulder.
It's like fiberglass on the inner structure.
There is a skeleton on the inside, a birch plywood skeleton.
Okay.
And the bolt, which is where a knot ties it to the rest of the vehicle when it's expelled. However, it is very light. It's got the fin, especially on the shoulder, it's thin, but it doesn't really matter because it's got a very strong bracing on the inside and it's got a lot of resin as well.
Okay. What is the strength limit for that eye bolt?
For the bolt,
basically, how much force could you put on that eye bolt before it fails?
I think we have written it on the technical report. We have a table. I don't remember here at the moment, but I'm pretty sure.
So I don't know. I don't so much need the number. More so, it's like, what is the factor of safety on that eye bolt?
I remember it's at least twice the load, but at least.
Okay, yeah, that's a good number. Knowing what force can be exerted on that is something that might be asked during the in-person safety reviews. Might not. It's just a good number to have on hand.
I think that's a pretty lightweight cone, so it would come off, but with low inertia, so it has not the force to tear apart the cord nor the bolt. It's that cord that we are
Okay,
using.
it's a shock cord. Is
Okay,
that 1 inch?
And just less, not 1 inch.
Okay.
It's like
That's nylon?
uh,
sorry.
Of 25 millimeters, so just slightly less than 1 inch.
What's the material for that shock cord?
Nylon.
Nylon webbing.
And let's see, you're using not black powder, CO2 deployment, so you don't need to protect the parachutes or the because there's no black powder, so no need for that, which is the nice part of using CO2.
Okay, here. That's the expulsion system and the two CO2 canisters. Cool.
Move it closer. What I'm seeing is off frame. So yeah, there you go. All right. Okay. So that's a 3D printed part there on the top. Is that printed in a similar method as the payload or the avionics bay?
The avionics?
It's like the same material, but it's not just a protection from the.
I mean, it's really mostly to keep the outside of the bay.
Here.
And
It's a very nice design.
avoid the contact between the hot resistance and the cords of the parachute, so they are separated mechanically.
Rotate it around so that I can see, because that right there, okay, so that's a similar eye bolt.
This is the quick release.
Actually looks bigger, so.
And if that system that cuts the rope that retains the main, this detached and just free. Here we have two redundant systems. Like one by one. The other
is one is a burn wire mechanical system that will capture the CO2 cartridge, and the other one is a and this one it's pyro system, and another needle and this. So some pyro is present, but only small quantities, just to not to pressurize the body, but only to rupture the seal.
Yeah, those are the primary and secondary for the deployment at Apogee.
No, the backup system, yeah.
Mm-hmm. Okay.
And for the primary parachute release, it's we have two systems. So also here, backup and the main. Our main system by us is and the hot system is used both on last flight.
And just to confirm, so the main chute comes out at Apogee, but it's held, not deployed until lower altitude using those.
It's deployed after.
Oh, so it's in the airframe still?
Yes.
Yeah. Because we have haven't one nose cone injection, but we have two. The first two deployments. The first is by the nose cone. When it pops out, it takes the drop parachute out. And the second event, and it happens like 400 meters above ground level, and
Sorry, I was just mumbling to myself. I was converting the meters to feet. Sorry, your audio keeps cutting in and out. Like I can still hear it all the time, but it goes from like I can hear it to I can only hear the echo, and I'm not entirely sure what's causing it.
Okay, I don't know why it's everything. So, any other questions?
A couple. Let's see. So I've left that. How big is your main parachute?
There you go. How big is our parachute? So, let's see. We have the parachute here. That's the drogue. Okay, that's the drogue.
That's the drogue.
Okay, it's like a
Cross street
Okay.
and size for 30 meters per second descent rate. There's a
Okay.
little bit smaller. Then we have the main. Now it's folded into the deployment bag, so we deploy it very easily and a good way with all the lines straight and not tangled each other. So. Okay. Then we have
Okay, yeah, that's the main orange and maroon, gold.
and three radios.
Well, they're also very different colors, so you can tell them apart.
That's a pretty good reason because
Mhm.
you can see the rocket in the sky well.
Yeah, black is going to be very visible.
Makes it pretty good, high contrast.
Hmm.
So this is size for and it's about 3 square meters surface. Little bit less.
Yeah, 3 meters in diameter, about 10
3
feet.
meters of square meters for the surface, the total area.
What's the descent rate under the main chute?
10 meters per second.
10 meters. Okay. Yep. Yeah, that's good. Okay. All right. Yeah, that's good on the parachute. Let's go back to the avionics bay real quick.
Just one moment.
No worries. I have plenty of experience in team settings dealing with large parachutes. And is one of the reasons why I borrowed the parachute I use for my L3. Mostly, well, and also big parachutes are expensive.
Just one question, but do you want to know something else about the air brakes before we continue?
The what?
Air brakes.
The air
Air
brakes?
brake system. Yeah.
Let's go on to that after the avionics bay. I just have a
Okay.
couple questions on that.
Okay. You can ask me.
So let's see. What vent holes do you have for your avionics bay?
It's analyzing the calculation of the mentals, but there will be 3 or 4 holes that are about 3 millimeters in diameter.
Okay. And those are equally spaced around the.
At the same level around the circumference.
Okay. Yeah, that sounds good. Where are your switch holes located?
I'm sorry?
Like for the altimeter switches?
Yeah, we have we don't have actual switches, but some connectors with wired that closes the circuit, and they are in the event scale behind one of the two panels.
So you are currently halfway out of frame from my viewpoint. So if you shift to the right.
That's way better.
Right.
Yeah, shift it a bit more to the right. There you go. Okay.
Right. So as I was saying, we have two female connectors on mounted on a plate that is in this area, and we have these connectors that are just 2x1 pins, and there's a cable that connects the two pins together. So when we insert the connector, it closes the circuit, and it acts as a safety switch. We chose some, the connectors are Molex nanofit series that have many security features, such as a locking mechanism and also a terminal position assurance that ensures that even by pulling the cable, it doesn't slide out from the connector itself, from the plastic housing of the connector.
All right. So by connecting the rocket together, that turns it on?
No. It's two electrical connectors.
Okay.
And after we connect these two, we will place the second shell of the avionics bay.
Okay. So there are panels on the electronics bay.
Yeah. It will be, this side will be permanently mounted. Then we will arm the electronics. Then we will place the second panel and there's.
So you can directly access the electronics bay while it's on the rail.
Yeah, because we have access to the two arming connectors and the connectors that powers our own avionics that are not connected to the expulsion system. So we have two cut system for redundancy, and then we have our avionics that will only log data for the flight, because it will be the second flight of the new PCB with new software, and so we weren't sure if it would be ready to be tasked with the deployment.
All right, and just to confirm, what are your avionics? What altimeters are you using?
So we're using a featherweight Blue Raven and a featherweight tracker.
Okay.
And then we have a CAT system Vega, that is an European board used by the Euro competition to track the flights that we already had. And it has the normal functions to deploy the parachutes, and also a tracker, GPS tracker that operates on 2.4 gigahertz that we will maintain switched off for the flight. So the only electromagnetic transmissions that we will do is by the featherweight tracker and the our own IREC tracker that operates that will operate on two different channels of the same frequency band.
All right. Let's see. It's peaking. So you mentioned that one of the panels is permanently attached.
Yeah. It's just that it is on the side that goes to the ramp, and so we can't detach it.
So that's the one that sits against the rail.
Yeah. So we could.
Rail buttons are on that line as well. Well, since that's the part that connects to the rail.
Yes, we don't have the rail buttons here because it would.
Where will they be located? Like you can just point to where the
show him the
rail buttons will be.
On the boat. So this is bulkhead we saw before about on the expulsion-based systems. So you can see these are M3 bolts which connect it to the outside frame, and itself is also connected through the 4 steel rods which run through the architecture. And on this plate as well, you can see there is an odd one out hole. So this is a larger hole compared to the M3s. It's an M4, and through this we will screw on the rail button.
Okay, so the upper rail button is all the way up
Nice.
above, just above the payload.
It's like
It's 20,
20
something like 20
centimeters.
centimeters above the top of the payload.
And
So
it's
this is the
here.
payload, and on top of here is the button. While
All right,
the
so
lower
that's the upper
button,
one.
Yeah.
yes, while the lower button will be located here, which is at the bottom of the air brake system. Again, you can see there's the bolts, which we talked about before, which hold it to the airframe. And there is an odd one out bolt hole, which once again is where you screw in an M4 pin, which holds onto the rail button.
Okay. All right. Let's see. Okay, so the connections, they're both screwing into metal, so there's no problems there. The locations. Okay. Let's see. So there's no rail button down by the fins because there's no real good way to screw that in.
Actually, there is.
There is one. Okay, so there's 3.
Yes, we could easily machine out one of these holes and make it an M4.
Uh-huh.
So actually, let me check out if, yes, it would work out.
Yeah, because usually the lower rail button is almost as low as you can get. It's usually connected to the fin can.
Actually,
Because the further ahead, that lower, let's see. What as we're on the subject of the rail buttons, what is your off the rail velocity?
At 30 meters per second. So
Wait,
we are
say that one more time.
35. The lower limit is 30.
Yeah, 35 meters per second. That's closing in on, I think, 120 feet per second.
Yeah, more or less.
Okay, and how is that calculated?
We have Rasaro files of the rocket that almost similar. And we have implemented a custom-made solver, 6-dot solver.
Mm-hmm.
And all 3 softwares give like the same result. So it's really on the spot.
Okay. Are you accounting for, so a big thing, and one of the reasons why I'm asking about it is there's a difference between the actual length of the rail, 17 feet, and the effective length. The effective length is basically because we want to know what the rail velocity is the instant the upper button leaves the rail. Because at that point, the rocket can rotate.
Okay, but if we fix another button down the fins.
Well, so the lower one, I just bring that up because I know some of the safety reviewers will probably be a bit iffy about having a rail button so high up on the rail.
Have another 2. So like the one here and the one on the fins, you are like 3/4 of the rocket that goes up, but the rocket doesn't.
Yeah, some safety reviewers are very iffy about anything that isn't like standard practice.
So
which
if you want, you can make another hole and.
Yeah, not saying that you have to. I'm not going to recommend that you add a fin button down by the fin can. I'm just saying that it might happen.
Okay,
it
so
just depends on the in-person safety reviews.
Okay, so just in case we
make one with an M4 hole, and maybe have to make the hole already bigger here. Maybe we can come down. When you were saying about the velocity when the first pin leaves the rail, wouldn't we get more effective distance by having the lowest spin higher up instead of lower down?
So the effective rail length that you use to determine what is your rail departure velocity given the first spin leaving the rail is you basically take the rail length, 5 point some odd meters, and you subtract the distance between your two rail buttons. So your rail buttons don't appear to be particularly far apart from each other. So you're probably only going to lose probably like half a meter or so, like 0.6 meters. That's usually average. In which case, because your rail velocity, like full tilt, is closing in on like it's 35 meters per second, you'd probably drop to maybe 32, 31 meters per second. In which case, you're already above the recommended value, even accounting for the difference in rail length. And even if your rail departure velocity dropped to say 28 meters per second, that would still be perfectly fine because you'd be well above the minimum required, which is 15 meters per second.
Okay, so 15 is like the lower minimum that.
Yeah, if a team were to submit a rail departure velocity of less than 15 meters per second, that would be a red flag and they'd be asked to correct it. Anywhere between 15 and 30, we just look for confirmation that the rocket will be stable. Since you're above the recommended, we're just like, okay, your rocket will be stable. And even if you drop just like a little below 30, it'll still be usually stable. We've seen plenty of rockets launch at 27, 28, 29 meters per second, and they fly perfectly straight, accounting for wind.
Yeah. Using considering also the wind. So differently software that on through the simulation zero angle of attack. We consider the angle of attack that we have at rail departure. That is the worst case scenario because the rocket is going very slow and you have the wind that is at 90 degrees. And even with an angle of attack 10 degrees, we are within the prescribed static margin.
Like in wind velocity terms, we can say that for a lateral wind of like 15 miles per hour, we have a static margin of about 2 calibers.
2 calibers? Okay, yeah, that's a good range. You don't want it to be too much, and obviously you don't want it to be too little. So yeah, 2 calibers is actually pretty good, particularly in 15 mile per hour winds.
That's like a great.
Yeah, if the winds at the launch site were to be consistently going over 15 miles per hour, we would be very careful about launching anything. I mean, the maximum limit is 20, but we're usually pretty, because if it's sustained 15, that means it's gusts over 20.
Okay,
so yeah, I think we're very careful about wind. But the fact that you can have that level of stability at 15 miles per hour, that is a very good sign.
At 20 miles per hour, we have just the minimum to depart. So
well, at 20 miles per hour, we shut down the range.
Or 20? No, it's not. It's not practical. So, okay.
All right. So I just have a couple more. What is your body tube made out of?
Fiberglass.
Fiberglass. And is that COTS or ESRA?
It's COTS. It's made custom by a shop. It's a pre-preg, which is rolled around a steel mandrel. Then it's cured in an oven, pulled out. It's machined to the exact outside diameter as well. So it's quite thick as well. We based so because we were able to specify the thickness and the inside we wanted. So we based it off the G12 standard, which we had used the previous year on the previous rocket, and it's actually even thicker than that.
Okay.
So we're quite confident.
All right. Yeah, that sounds good. All right. Let's say the last part for the body tube is you will need the team name, number, and frequencies on the outside of the rocket. That's just for identification. Both when you recover it, if anyone else is around, and also on the live stream. Okay. All right, so a couple more. What motor have you selected?
Cesaroni M1830.
Motor. And you're planning on using the igniter that comes with it?
I think, yeah.
Yeah, yes is
I
a good
don't
answer.
actually know because the motor, the 4 has the motor. So I think we have an igniter. So
yeah, because so you've ordered the motor, but it'll be picked up by your flyer of record.
The motor is already at home. The flyer of record. So it will bring
so he has it. All right.
Yeah.
And that last one, I don't need to ask. Okay, am I missing anything? Oh yeah, let's take a look at your air brake. It's not technically like part of my checklist, but our team tried to fly an air brake when I was a competitor. We don't know if it worked or not.
Okay. And just now, the air brakes are internally dismounted. So if you see just,
I can see the slots though.
That if you see the pedals come out, it's because internally it's not mounted anything. But just an overview of the system. That's a 2-block. It's pretty heavy. That's two block aluminum made air brake system.
See, if I could speak. So you've put the air brakes into the aluminum coupler between the airframe sections.
The coupler is the air brake system. It does. So
Plus, it's like it also means you don't have to cut slots into the airframe material.
It's not. Well, it's different.
And the coupler starts just
Yeah, your audio. Whoever's speaking, your audio cuts in and out because you're not facing the camera.
Okay. Yeah.
So these are backup pieces for the air brake system. So this is the bottom half. So this is milled solid aluminum 6061.
And that's the top part. So the slots you see are like not really slots, but just close
Very
together.
well machined. High quality machining.
That's pretty tough also. So okay. Fine.
So this is the bottom half, which is the one that leads onto the lower body frame, while this is the above piece, which is used to hold onto the 2 shell plates.
Okay. Yeah, and those holes are for connecting the panels for the avionics bay.
Correct.
Yeah.
Also,
Okay.
So it's like a solid piece of aluminum and
quite hefty as well.
So it has a structural function, but we have as usual the rods. So the bending loads, we can say, are beared by the steel rods. So we made some calculations, and we have like the maximum bending moment in flight that it's 120 Newton meters. And we have a factor of safety of 3, 4, 5 even. I don't remember well, but it's it can hold the load. Are these okay? I think you want to know something about the system of the pedals. So
how many individual air brakes are there?
There's no individual air brakes.
Okay.
One moment,
like how many unique pieces come out of the airframe when you actuate the air brakes?
We're gonna be switching to me for this part.
Okay.
So it's 4 petals. So it's 4 individual aluminum plates which pop out or orthogonally to the airstream. But however, they are moved by a cam like this.
Okay, that was my next question: is how they were actuated.
So they're only allowed to move together. So there is no possibility for asymmetric deployment. So this means that also, if, for instance, in a failure, if the cam were to jam, or for instance, if there were to be a power loss with the air brakes half deployed, they would stay half deployed symmetrically, meaning you have no moments on the vehicle.
So do you just have so you twist that that piece of metal, you just rotate that?
Yes.
The actuator just rotates that, and that
exactly.
deploys
so
or retracts it.
Yes, we've got the servo motor, and we've got linear rails with a pin that rides inside this groove, which is moved, and as such, after a 90-degree rotation, we've got full deployment.
That's actually a very, I like that design. It's very elegant.
Back to you, Massimo.
All right. Okay, yeah, so that answers most of my questions safety-wise regarding the air brakes. But also,
just one thing, we didn't. We are, okay, can you repeat? We hadn't the audio. You can repeat the question, because we lost the audio for a second.
Yeah, sorry about that. What lockouts do you have to prevent the air brakes from deploying while the motor is burning? So during the boost phase, what lockouts do you have to prevent the air brakes from deploying?
Answer this question. So there's the servo motor that keeps them closed. With the system that my colleague showed you, even with a great load applied, the air brakes cannot be opened by themselves.
Okay.
The servo motor has to rotate to deploy the air brakes. And
so vibrations won't do it.
Sorry?
So vibrations won't deploy them.
Yeah, exactly. And even if this rod avionics loses power, the friction inside of the servo motor will keep them closed. So vibrations are not a concern, not even the a very exaggerated spin of the rocket can open the air brakes. And as we were saying, even if they deploy, they will be perfectly symmetrical. And we did the calculation CFD and FEM for the whole flight envelope. So even though we will deploy them after Mach 0.7 or 0.8 during the deceleration phase, and we are still debating the exact figure, but we have tested the structure, and it will resist even if it deploys at maximum Q, so at the maximum velocity that we reach during the flight.
Yeah, so in terms of like conditions for activation, you'd probably want to look for time, because the motor has a specific burn time. So if you're going beyond that, then the motor should have burnt out by that point. You could look at speed, because once you get to a maximum speed and you start dropping down again, then the motor is burned out. You could also look at acceleration. So when the motor, of course, ignites, there's going to be a rapid spike in acceleration, and that's detectable. When the motor burns out, there's going to be a drop in acceleration, and that's also detectable.
Yeah, actually,
so what we're looking for is a set of conditions, software-wise, that will prevent the air brakes from deploying while the motor is burning, because you can't deploy air brakes while the engine is lit.
Okay, I can answer you right now, and then we will have something written if the questions is repeated on site. So we have a Kalman filter that fuses the input from the accelerometer, gyroscopes, barometer, and magnetometer, and it gives an estimate of the state of the rocket that is quite resilient to spikes in pressure and noises in general. Also, we have a state that we can look for the velocity when it descends under a certain threshold, and we will activate the aero brakes after that threshold is after we meet the threshold. Also, I think we were going to implement a timer that starts, as you suggested, starts at motor ignition, and it inhibits the opening of the aero brakes for a little bit more than the standard duration of the burn time of the model. So maybe we'll wait 1 second or around that period after the burnout, and then we will open the aero brakes. We will enable the standard decision process to enable the aero brakes. So it will be two conditions to be both met to enable the deployment.
Okay. Yeah, that sounds good. All right. Perfect. All right. So let's see. Do I have anything else? Okay, all those sections are complete. All right. So the only other things I have. Let's see. The rocket is present. Is your rocket currently in a launchable state, or how close would you say it is?
Almost, because we have a test flight like next week on 10th of May, so like really in a week. So at the moment it's like 90% complete, like almost flyable. But in a week it will be ready. So by the end of May,
Less than a week it will have flown as well.
Hopefully, yeah. So we are like on point.
All right. Yeah, that's good. It'll definitely be ready by the time of the competition in about a month.
Yeah,
5 weeks.
So, the state of rocket, so I think it's great. So the same.
Perfect. All right. I don't know if you saw the meeting that was this Thursday, but there will be tents and tables provided, just as with last year. So the only thing that you need to bring are tables, or not tables, chairs, if you want chairs. That's the only thing, other than your like team stuff, like your rocket, your supplies, that sort of thing.
The camping chairs would be nice to.
Yeah, so if you want chairs, bring chairs. I read through your progress report, so like your hotel, you've got that set up. Visas are good. Yes. So like being able to go to the US, you have that all sorted out.
Okay, so it's a green light.
Uh-huh. All right. Just as with Las Cruces, it gets quite hot in Midland because it is the southern US. So sunscreen, water, you're in a desert, so plan accordingly. Yeah, so food and water is the same thing as with the chairs. Let's see. Just as a warning, there probably won't be the case, but don't paint your rocket in Airbnbs, hotels, or at the convention center. Try and do that. So, do that in a place where it's actually good to do painting, that sort of thing.
Still in Italy, so no problem.
Okay. All team members that go past the flight line will need to be members of EEE. So you'll need EEE numbers for everyone who goes past the flight line. Does anything on your rocket require a ham license?
No.
Okay, then you don't need to worry about that. Okay. So the last thing I have on here is be smart about everything you do. Be safe. We don't want any students to be in danger of anything. We definitely want students to have fun. That's one of the primary purposes of this competition. And that is everything. All right. Do you have any questions for me before we?
Okay. Me personally, no.
I haven't checked recently, but is there a document that specifies the exact position and azimuth and inclination of the launch ramps that we will fly from? Or is it
like orientation to the launch rails?
Yeah.
So
Orientation
typically the launch rails are orientated so if they do have an angle, which they will, they are angled into the wind, or
Right.
so that basically they're pointed away from the student area and basically where all the people are, so that the rocket, when it angles, because it is at an angle, it angles over away from the populated areas of the launch site. The angle itself is typically, so it's usually between 2 and around 6 to 7 degrees. We usually set it to around 4 or 5 degrees.
Right, but do we have a say in the exact angle that is set, or is it something that is imposed by you?
It's normally imposed. So we usually set all the rockets to be at the same angle.
Right, and will it be known with I don't know, maybe a couple hours of time beforehand, so that we can rerun our simulations and adjust some parameters?
I can double check, but it's usually about 4 to 5 degrees.
Right.
Another question regarding the time that the time interval that the rocket will spend on ramp. Usually, like we have to wait a lot of time, like 2, 3, 4 hours, or a little less.
Between setting it up and launching it?
Yeah.
We usually, it depends on when in the salvo you are. Typically a salvo lasts about 30 to 40 minutes, closer to 30 minutes to launch, like from the first rocket launch to the last one. We usually try and keep it pretty quick. From setting, like when leaving the pad, when you set it up to the salvo starting, we usually try and keep that to less than 15 minutes. So basically it's like the whole process of getting rockets on, like at the pads, to setting them up to everyone leaving, we usually try and keep that within an hour if we can, hour to 2 hours. Between turning on avionics, installing the igniter, and then everyone leaving, and then the salvo starting, is usually less than 30 to 40 minutes.
Okay.
Because once all the rockets are, like, once you've turned on the avionics, once you've installed the igniters, you have 20 rockets, all with igniters, and a lot of them with black powder charges. So we usually want to get all the avionics working, the igniters installed, and then everyone leaving as quickly as possible.
Yeah, because we don't have black powder, but we had a problem, like sort of problem, not like a real problem. But the CO2 cartridges, if heated, they will not explode, obviously, but it's not optimal.
Okay. Yeah. The whole process of getting all the rockets at the pads, installing them, getting everyone off, and then launching the entire salvo should take less than 2 to 3 hours.
Perfect.
Optimally. In worst case, it's 4-ish. But that highly depends on weather and how quickly everyone gets their rocket set up.
We can stand 4 hours.
Can you give an estimate of how long does it take to recover the rocket after it is launched? It obviously depends.
As long as the rocket doesn't go too far away, you should be able to recover the rocket within 2 to 3 hours, if not much faster. Because if you're using with dual deployment and low winds, the rocket will land within a mile or 2 of the launch pad. And because everyone has tracking, you will know exactly where it is. So most teams can just drive off to where the rocket is, pick it up, and then come back.
And we are allowed to go after the rocket as soon as the salvo ends?
Yeah, so there is a separate recovery process. And And you'll want to look up the recovery process for that, because there are procedures and who can go out, and it might be a bit different because we're not at spaceport anymore, but I'll probably want to see on the recovery process, particularly since we just barely like this is the first time we've ever launched here, so a lot of the stuff is kind of up in the air, but I'll check on that as well to see, because you will not be, every team will want to know what the recovery process is, so I'll check on that. Any other questions?
No, yeah, fine.
All right, fantastic. All right, so this has been recorded. You will need to send this to general.info. Let's see. Yeah, general.info at ESRArocket.org will be the email address you send the recording to as an MP4.
Same address that we contact every time. So okay, it's okay to share the video like on Dropbox or a Google Drive, because
yeah, I mean the recording will be big enough that if you try and email it, it will send it as a link. So
yeah. So Google Drive just
yeah, as long as you send the link or how to access it to general.info, that email address, it should be fine. If not, they will tell you.
Okay.
So yeah, that's the only other part you have left.
So I think we don't have any other questions.
And I will get positive contact with Adam in regards to him as the flyer record. I'll probably just message him.
Okay, because it's strange.
Probably direct message him. I don't know why he didn't he didn't respond to my text message, so I'll just message him.
Because I had the email that I contacted him yesterday or 2 days ago, but I shared the link with him. Well, even better, I contacted him first to ask information about the flight readiness review, and he told me to write to you. So I proposed to him a time that was the same that I proposed to you. So I don't know. It's a bit strange, but
yeah, I'll message him just to confirm that he's all right with the design as it currently stands. I have a process for if the flyer record isn't at the meeting.
Okay. So, just in case, I think we will get an email from Adam, and but I'm pretty sure he will be okay with the design. We have discussed a lot in the past few months, so
that is also good to hear. So, in that case, yeah, so send the recording. I'll contact Adam. I'll check on the 2 things I have written there, and you guys are all set.
Great.
Yeah.
Oh, and just in case, I have recorded this meeting as well.
Okay, perfect. Because we have 2 recordings.
Mine is
the backup, just in case.
When you're recording, the backup and the other backup. Okay. Good to hear. So we are all set.
Yep, you're all set. Just email that recording, and I'll take care of the stuff that I'll take care of, and I will see you guys at the competition.
See you in Texas.
Great.
See you.
Bye.
Bye.